Hello everyone. Today we have Chinmay Dharmendra from University of Connecticut, and he is going to be talking about homomesies. Before we start, let's recall our guidelines. We're all learning, everyone has something to contribute, and no one has all the answers. With that, Chinmay, take it away.
Thank you so much for the introduction, and thank you to all the organizers for organizing this. Um, and thanks for everyone in the audience for coming. So I'll be talking about homomesies of linear feedback shifts, and this is joint work with Matthew Plant and Tom Roby. So first, let me define what a homomesy is. This is a very important phenomenon in dynamical algebraic combinatorics. So if I have a set and I have an action acting on the set, you can also think of this as a group acting on the set, such that every orbit of the action is finite. And given a statistic, mapping to generally a field, then we say that the statistic is homomesic with average C if the average of that statistic across every orbit is the same. So you take the sum of the statistic throughout the orbit. You do this for every orbit, divided by the size of the orbit. And if this is a constant for all orbits, then we say that the statistic is C-mesic. In this talk, so this isn't too common in the literature, but it comes up in some places, I also say that lambda is equivalent to C. And this will make sense because expectations are linear. You can add and subtract them in linear ways. So this is just a nice way to represent that. So just a quick example of a homomesy. So if my set is the set of binary strings with length n and k ones, and if my action is the cyclic rotation of my string to the right, and my statistic is inversions. So what is an inversion? It's the number of times a 0 occurs after a 1 in a binary string. It means something different in the context of permutations, but this is a generalized definition. So this is just our string rotating 0, 0, 0, 1, 0, 1 to the right, giving, so this one comes all the way here and everything else shifts one stage to the right. And the number of inversions of this statistic. So we get 4 inversions from the red one because there are 4 zeros appearing after it, and 1 0 after the blue one because we have 1 0 appearing after that. So the total number of inversions for this is 5. So a result of Prop and Roby says that the statistic of inversions is homomesic with average k times n minus k over 2 with respect to the cyclic rotation on bit strings of length n and with having k number of ones. And then here we can see an example. So when we add across everything in the orbit, we should get the average to be 4. So if you want to add across this, you should get 24 here, 24 here, divide by 6, you get 4. And here when you add, you get 12, divide by 3, you get 4. Yep. So now I'll define the action that we'll be studying. So this is actually motivated from computer science, in which they care about linear feedback shift registers. So linear feedback shift register is an array of bit strings. So you have one bit string, one after the other, such that each subsequent bit string is derived from the previous bit string with some sort of linear transformation. And the one that's been used in, I think, the most number of implementations is called the Fibonacci linear feedback shift. So what it does so we can also consider our bit strings as vectors in F to n, the field of characteristic 2 elements, the vector space of dimension n defined over that. So we define our Fibonacci linear feedback shift to be a sort of modification of the rightward cyclic shift, where it takes f alpha of x1, x2, x1, xn minus 1, xn, shifts everything else everything one step to the right, x1 here, but for the first coordinate that usually would be derived from xn, we instead get it by alpha dot x, the dot product in f2. So I'll show an example, but there's also a logic gate representation we have here if if any of you are familiar with that. So we see that our alpha here is 0, 0, 1, 0, 1, 0, 1, 1. And we're feeding in the data from the third, fifth, seventh, and eighth entries into our logic gates to derive the new entry. So these have been used a lot in computer science, as they've been mentioned, mostly in pseudo random number generation. And the coolest use, in my opinion, is that it's used for pseudo random number generation in Tetris. So if you get into a certain seed, you just get the same block over and over again. So here's an example. Our alpha is 0, 1, 1, 0, 0, 0, 0, 1, 1. And the corresponding elements are highlighted in our string X. So to get the first entry, we just take the sum of all the highlighted entries in F2. And that's just going to be 1. Because if you add up an odd number of ones, you get 1. And every other entry is just gotten by cyclically rotating to the right. So similarly here, to get the next entry, 1, 0, 1 plus 0 plus 0 plus 1, we get 0. And every other entry is gotten by cyclically rotating to the right. Okay, and then again, 1, 1, 0, 0, 0. And again, and you can see that everything else is just gotten by rotating to the right. So yeah, it's not too different from the rightward cyclic shift, but it is different in a number of key ways. So in dynamical algebraic combinatorics, we like studying a few things, and when they come up, I'll mention how they're different. But the first way is the matrix. So since it's a slightly modified rightward cyclic shift, it's very similar to the matrix of the linear action is very similar to the matrix of the rightward cyclic shift action. So remember that in the rightward cyclic shift action, the first row would be 0, 0, all zeros, and then 1 at the end. For our Fibonacci linear feedback shift, we just replace the first row with our string alpha. So we call this the companion matrix of the action f alpha. And if we just consider our bit strings to be vectors in f2 of n, then the action can just be described as f times x, just a matrix action. The characteristic polynomial of f is also very nice, in my opinion. You just have a leading coefficient of x to the n. And then to get the rest of the terms, you just read out alpha with the corresponding n minus I power. So x to the n plus alpha 1 times x to the n minus 1, alpha 2 times x to the n minus 2, and so on and so forth. And any matrix that's set up like this has the good property that the characteristic polynomial is also its minimal polynomial. And that helps in proofs a lot. So just some examples. When we look at the rightward cyclic shift, this is the action we get. We can represent a rightward cyclic shift as a Fibonacci linear feedback shift with alpha is equal to en. So we are able to, so this is really a generalization of a rightward cyclic shift. And the characteristic polynomial will just be x to the 5 plus x to the 5th power plus 1. Just one thing I forgot to mention, that this characteristic polynomial is also in f2 of x. So just remember that when we're going through this talk. And if we instead have alpha is equal to 1, 0, 0, 1, 1, all we do is replace the first row with 1, 0, 0, 1, 1. And then we get the characteristic polynomial x to the 5 plus 1 times x to the 4 plus 0 times x to the 3 plus 0 times x squared plus 1 times x plus 1. And so it's once you have alpha, it's very easy to get the characteristic polynomial. In this action, the order of our matrix, so the order being the small positive integer such that f to the k is equal to I, is also the length of the longest orbit of f alpha. When you have actions derived from groups, that's not always the case. Usually it can be anything dividing the LCM of all the orders of all elements, but in this case we do get the longest orbit. Do this. So I've been saying that this is our action a lot, but the word action in this field usually implies that the action is invertible. But in this case, it's not always invertible. So if we go back to the matrix, if alpha n was equal to 0, I'd have a 0 column. This would definitely not be an invertible matrix. So we specify that we need alpha n to be equal to 1. So you can see this from the matrix, but you can also get this just from the description of the action. We're doing a rightward cyclic shift. At each stage, we're kicking out the last element. If we don't use the last element to get the new information, then there's no chance of it being invertible, because it would have come back from two states, one with the last element being 1 and one with the last element being 0. Okay, so this is something that we'll be using a lot. The sum of digits of alpha and f2. So this is basically returning whether the parity of the number of ones in our string alpha, or any binary string in f2 again. So in example here, this string 10011 has 3 ones, so it returns 1. And this string 111010 has 4 ones, so it returns 0. So one thing that we really like in studying in dynamical algebraic combinatorics is the orbit structure of an action. And the most basic orbit is a fixed point. So since this is a linear action, the 0 vector will always be a fixed point. If you multiply any matrix with a 0 vector, you just get 0. And whenever the number of ones in alpha is odd, then the vector of all ones is also a fixed point. So we get that very nice property. But unfortunately, it's not always interesting to study the dynamics of actions with fixed points, at least in the context of homomesies. But both in computer science and just naturally, there's another action that is slightly more interesting. So we call it the affine Fibonacci linear feedback shift. And what we do at each stage is we choose a string beta, and at every step of our action, we just add on beta to our f alpha string. So if you're more familiar with computer science, you can think of it as kind of a masking binary string. It makes our action look less like a cyclic shift, if that makes sense. So yeah, that can be helpful in computer science. And we can see that the way we define the action f alpha beta of x is just equal to the Fibonacci linear feedback shift and adding a fixed vector at each step. So the reason we call it an affine action is because it's an affine action. F alpha beta of x is equal to f of x plus beta. And if applying it k times, we get f alpha beta the ith time. If you do it this I times, you get fi of x plus sk beta, where sk is the successive sums of our matrix from I to k minus 1. So when we write sk, it's important to remember that this is still a successor. This is still being derived by our original matrix. So we have an example here. Our alpha is 100011, our beta is 100110, and our x is 110101. So first, we try to apply f alpha beta to our string. First, we need to apply f alpha. So to do that, we highlight the entries that get added to derive the first new entry here. So 1 plus 0 plus 1 is 0. We cyclically rotate everything else to get the rest of the string. We add our beta, and that's how we get the result of f alpha beta of x. So we won't have much luck finding homomesies of f alpha. So let's see if we can do anything with alpha of beta. So what we want to do is classify all our f alpha betas by their dynamics. So these f alpha beta pairs have nice dynamics. These f alpha beta pairs have so-so dynamics, and so on. And our first step is figuring out how many fixed points the actions have. Is there a nice condition for this? And yes, there is. So first we define an operator called the discriminant. So given an alpha and beta in Fn, we can define our discriminant to be the dot product of alpha check dot beta. So what alpha check is we take the partial sums of alpha from starting at that element. So the first entry of alpha check will just be the sum of all elements of alpha in F2, of course. The second entry will be the sum of all entries in alpha starting at alpha 2 and so on and so forth. So in our example, our alpha is 1, 1, 0, 1. So calculating alpha check, the first entry will be 1 plus 1 plus 0 plus 1. That gives us 1. Second entry, 1, 0, 1, gives us 0. The third entry gives us 0 plus 1. This gives us 1. And the last entry gives us 1. And when we take the dot product of alpha check plus beta, we get the result for our discriminant, d alpha beta equal to 1. So why do we care about this pretty random operator, this random statistic we just defined? Well, for one, alpha check is actually the Greek code of alpha, which is another computer science kind of term. But also, it just gives us how many fixed point interaction, how many fixed points our alpha beta action has pretty directly. So whenever the number of ones in alpha is even, the action has exactly one fixed point. Whenever the discriminant is 0, but the number of ones in alpha is odd, that action has no fixed points. And the important thing is, whenever the sum of digits in alpha is odd and the discriminant is 1, that action has no fixed points. And these cases will be the interesting ones that you want to study. So for all n greater than 3, there are exactly half of beta will make the discriminant of alpha and beta. So sorry, let me rephrase that. When n is greater than or equal to 3, for each alpha, exactly half the available beta strings will make it so that d alpha beta is equal to 1. So we're not like hurting for the strings that have d alpha beta is equal to 1. So whenever alpha n is equal to 1, the discriminant of alpha and en is equal to 1. And whenever the sum of digits in alpha is odd, d alpha of e1 is equal to 1. So those are two cases that you always know you have. And a nice lemma tells us that whenever you have an invertible Fibonacci linear feedback shift with the discriminant being 1, then instead of just studying the dynamics of f alpha beta for each beta, it's enough to just study the dynamics of f alpha of en. Because every orbit of f alpha beta will just be a translation of an orbit of f alpha of en. And since the proof is pretty short and kind of fun, I just wanted to sketch it out. So if d alpha beta is equal to 1, then if you have the definition, try to convince yourself that d alpha of beta minus en is equal to 0. So all these operations are in F2, so minus is equal to plus as well. But it's a bit more evocative if I have it as a minus. So from our theorem, whenever d alpha beta is equal to 0, remember, okay, sorry, I'm missing a clause in this theorem. The sum of alpha should also be 1 here. Yeah, so whenever d alpha of beta is equal to 0, I know my action has a fixed point. So the f alpha beta minus en action, has a fixed point, say w. And if v is another vector, then let's examine the orbit of f alpha beta containing v. So applying the action any number of times, our orbit looks like this, si of v plus si of beta. So let's rewrite the orbit. These are all linear, so we can do this. We define a z vector to be v minus w. So this splits into fi of v plus fi of w plus si of beta minus en plus si of en. This should be down, sorry. A lot of typos in this slide. So let's regroup them. We get Fi of W plus Si of beta minus En plus Fi of Z plus Si of En. But remember, W is the fixed point of the F alpha beta minus En action. So if you have a fixed point, no matter how many times you apply the action to that point, it'll just stay the same. So this whole thing is just W plus Fi of Z plus Si of En. This, taking W out for all things, we just get W plus Fi of Z plus Si of En. And note that this set is just the orbit of Z in the F alpha En action. So this is a translation of the orbit. A lot of dynamics that you have over if of a lot of dynamics of F alpha of En will just translate directly to F alpha of beta, since the orbits are just translations. For one thing, the orbit structure, if you want to know the length of each orbit, that is definitely going to be preserved when each of the orbits is a translation of something of another orbit. So you can actually say something a bit stronger, that the orbit structure of any vector, any action d alpha of beta 1 and d and f alpha of beta 2, if d alpha of beta 1 is equal to 1 and d alpha of beta 2 is equal to 1, then they also have the same orbit structure. Okay. So this is nice. It really cuts down on the number of things you have to study. So when we're studying homomesies, we want to study a particular statistic. And probably the most basic one to work on is the indicator function. So the indicator function just looks at the ith position in the bit string and returns it. So here, the indicator function at 3 is just looking at the third position and returning 0. And yeah, it's not too bad to look at. It's a very natural function, and it gives us some nice results. So remember when I said that this is a modification of a cyclic action. So we get a lot of things for free just because it's a modified cyclic action. So for F alpha beta, we always get the set of n minus 1 homomesies. So if you fix a beta, then you'll always get, whenever I is between 2 and n, chi I minus 1 is homomesic to 0. So what this is saying in plain English is that if you look at the whole orbit, the number of ones that appear in the first position is exactly equal to the number of ones that appear in the second position, if beta 1 was equal to 0, and so on and so forth. And chi I plus chi I minus 1 is homomesic to 1 if beta I is equal to 1. This is just saying that the number of ones in the ith column is exactly going to be equal to the total number of zeros in the I minus 1 column, and vice versa. Okay. So we get these for free. You can kind of imagine an entry just going through the orbit only being interacted with the betas. Remember that alpha only affects the first entry. So that's why all of these depend only on beta. Okay. So this action has been used in pseudo-random number generation. What's a very natural homomesy that one would think of? Well, for us, it was, when is the number of ones equal to the number of zeros in each position of the orbit? For any of the positions, it turns out that because of these cyclic homomesies, if the number of ones is equal to the number of zeros in any position of your orbit, then it's true for every position. So the homomesy we're looking at is chi I is homomesic to 1/2, and for all positions. So when are the number of ones in every column equal to the number of zeros in that same column? So whenever this happens, we say that F alpha beta exhibits the equal expected value homomesy. So one thing to note is that if f alpha beta has fixed points, this isn't possible because there's only one element in the orbit. There's no way that the average can be half, right? So this is why we care so much about fixed points. We can immediately discard everything, every alpha beta action that has fixed points. Sorry. So this is an example of something that exhibits the equal expected value homomesy. Alpha is equal to 1, 0, 1, 1, and beta is equal to 1, 1, 1, 0. So if we look at the first column, we can see that the number of ones is equal to the number of zeros. And the same is true for every column. One thing I want to call out here is that our first vector is 1, 1, 1, 1. This is an orbit of length 12. Our seventh vector is 0, 0, 0, 0. And if you keep looking at the orbit, you'll see that exactly halfway through, we get the complement of the corresponding vector. And it's easier to see in the shorter orbit. So something is going on here. And that's what we have to try to investigate. So initially we thought, okay, is it just the discriminant whenever the action doesn't have fixed points? Is that enough? Turns out no. This action is such that our f alpha beta has no fixed points. So if you look at the first two orbits, everything's fine. You get something nice. But if you look at the orbits here, look at the first column, we're out of luck. It doesn't quite work. And one thing to note is that for any vector in this string here, you can find the complement in the orbit, in the second orbit. And for any vector in the third orbit, you can find its complement in the fourth orbit. So what happens is, given an f alpha beta with no fixed points, or even with fixed points, you can fall into two cases. Either the complement exists in the orbit for every vector, or you have an orbit and you have a separate orbit that is exactly the complement of the first orbit. And those are the two cases we're falling in, and that's what we try to figure out. When does each thing happen? And we can do this, and surprisingly, it's a polynomial condition. So there are actually quite a few conditions that lead to the same thing, but this is the only one that we could find that only depended that you could get without computing anything else other than just looking at alpha and beta. So every other condition we had needed us to compute one orbit or compute iterations of a matrix until it got back to the identity. But this is rather clean, and it doesn't send us out to do all that headache. So if you have in alpha and beta belonging to f2n, with alpha n is equal to 1, the number of ones in alpha being odd, and the discriminant of alpha and beta equal to 1. So basically, if you have an invertible action with no fixed points, and if p alpha of x is the characteristic polynomial of f alpha, we look at its irreducible decomposition in f2 of x. So since alpha n is equal to 1, you always have at least one factor of x minus 1. So x minus 1 with multiplicity r and some other irreducible factors with multiplicity si. So note that none of these irreducible factors can ever be x, because then our action would not be invertible. So it turns out that whenever r, the multiplicity of x minus 1, is a power of 2, and whenever it is the greatest multiplicity, so both of these conditions have to be true, then our f alpha beta exhibits the equal expected value homomesy. So our conjecture, and this is a very strong conjecture because we think we're pretty close to getting it, but we've been working on this on and off, so you know how that goes, that this condition is also necessary. So this condition exactly tells you when two orbits that are complements of each other merge together, in this case. And whenever it doesn't happen, you get something like this, where the complemented orbits stay separate. So just a few examples here. Let's look at our previous example. The polynomial ends up decomposing in f2 of x to x minus 1 power 5. So since we're in f2, is also x plus 1 power 5, but if you generalize to different fields, it's better to keep it as x minus 1. So the multiplicity of x minus 1 is not a power of 2, so this one does not work. Okay, and this is the other condition. If our alpha is 1, 1, 1, 1, 1, beta can be anything that keeps the alpha beta equal to 1. P alpha of x is equal to x minus 1 times x squared plus x plus 1 whole squared. So x minus 1 does not have the highest multiplicity, so this doesn't work. So I just want to call out something here, that this orbit is complemented. So it's not that every orbit cannot have its complement within itself, but so yeah, everything here, these orbits also have the vector and its complement within it. But the first orbit and the second orbit, we have no such luck. So we can see that the number of ones and zeros are definitely not equal. Yep. And our last example is when it works. I haven't written out all these strings since it would be 64, but when p of x is equal to x power 6 plus x power 5 plus x plus 1, then we break down into x minus 1 squared times x power 4 plus x cubed plus x squared plus x plus 1. And here f alpha beta does exhibit the equal expected value homomesy. Yeah, so whenever this happens, we know for sure we get it. We don't have a tight proof that this is necessary, but we strongly believe it. We strongly believe it's necessary. Okay. So this would be a good chance to ask for questions. Does anyone have a question? Okay, let's move on then. So one of the reasons we really wanted to get a condition that only looked at alpha and beta and didn't have to do anything like, okay, the order of this matrix is k, let's look at some other stuff, is because it's much easier to count and classify for each n with this condition. So so here n is just our numbers, and dn is the number of alphas such that f alpha of en exhibits the equal expected value homomesy. And if you can kind of see that once we get to a point, it kind of like starts doubling at each stage. So as the powers of 2 get further and further apart, the growth of the sequence is approximates doubling more and more. You get bad behavior near the powers of 2. So for every power of 2, you pick up a few more strings. And right before a power of 2, you pick up a lot less strings. But yeah, the growth is definitely of the order 2 power n. But we don't really have a nice formula for like when things are slightly off. So because we have a condition for polynomials, this one, where the study of counting polynomials has been studied extensively, and we get a kind of generating function. So this isn't the nicest generating function because it's not just one closed form. Instead, we're taking the sum of many generating functions. So at each I, the generating function is just counting how many polynomials have such that the multiplicity of x minus 1 is equal to 2 to the I, and every other distinct irreducible factor has multiplicity less than or equal to I. But even though this is not the nicest generating function, if you want to get the coefficient for t to the m, we still only have to compute the sum up to log 2m term, log m to the base 2 terms. So it's pretty fast to compute this series using this generating function. All right. So that's about all we have for Fibonacci linear feedback shifts. But in other, I'd say more interesting feedback shift is the Galois linear feedback shift. So it's a bit harder to define, but the Galois linear feedback shift, the parameter alpha. So we have modeled this on so this is known in the literature, of course, but like in our specific case, we model it on a leftward cyclic shift. So you see here, G alpha of x1, x2, xn minus 1, xn. You have an x2 here, an x3 here, an xn here, and something here. And then instead of only affecting one element, which in this case, the entry we kicked out is the first element, and then we have a vacant space of the last element, we actually affect the whole string. So this is just saying that if x1 was equal to 1 in our string, we add alpha to our string. And if x1 is equal to 0, we just keep it the same. So let's look at the orbit as an example. Here we have 0, 0, 0, 0, 1. x1 is equal to 0. This just goes to 0, 0, 0, 1, 0. And it keeps going like this. But as soon as the first entry in our string is 1, we have to add our alpha, which is 1, 1, 1, 1, 1. And the reason I like alpha being equal to 1, 1, 1, 1, 1, 1 so much is that it just flips everything. It just takes the complement of the rotated string. So when you rotate it out, you get all zeros, and then it flips to all ones. And we've seen this type of action in other dynamics, kind of, mostly toggling actions, where you start as a cyclic shift, but as soon as there's an element at the right edge or the left edge, your action changes. And that's the kind of action the Galois shift is. So even here, if we start at 1, 0, 1, 0, 0, we rotate it here, we'd get 0, 1, 0, 0, 0, and then we flip it to 1, 0, 1, 1, 1. Sorry, I know it could be a bit confusing, but I'm just like saying a bunch of ones and zeros at you. Thank you for staying with me. So yeah. The important thing to remember is that whenever x1 is equal to 0, it's just a leftward cyclic shift. The upshot of defining it this way, so the other way in the literature that you define it is as a rightward cyclic shift with similar actions, is that the companion matrix of the Galois linear feedback shift ends up just being the transpose of the matrix for the Fibonacci linear feedback shift. So we get with the same characteristic polynomial, of course. So we get a lot of nice analogous results. And the invertible, of course, it's only invertible if alpha n is equal to 0. You would get a 0 row instead of a 0 column. In this case, even though we are kicking out the first entry, it's always used in deriving the new information. Just by the definition, we have x1 in every element. So there's no problem with alpha 1 being equal to 1. Okay, so why is it called a Galois linear feedback shift? So we didn't name it. This is already known mostly by computer sciences. I'm assuming they named it a Galois linear feedback shift because it has polynomials in it. So a Galois linear feedback shift is just multiplication by x in the quotient ring of f2 of n of x over p alpha of x. And the bit strings correspond to the vectors with the basis x minus 1, x minus x to n minus 2, all the way till n minus 1. So we have an example that illustrates it a bit more clearly. If alpha is equal to 1, 0, 1, 0, 1, and this is our p alpha of x to the fifth plus x to the fourth plus x squared plus 1. So when we apply this to 1, 1, 1, 0, 0, this is our answer, 0, 1, 1, 0, 1. And when we multiply it by x, we get x times x power 4 plus x cubed plus x squared. This is equal to x power 5 plus x power 4 plus x cubed. But in our quotient ring, x power 5 is equal to x power 4 plus x squared plus 1. So we just replace it with that. After doing our addition x2, we get x cubed in f2, sorry, not x2. We get x cubed plus x squared plus 1. And that's exactly corresponds to the string we got here. So this is nice. It has natural applications to algebra. Thinking of the Fibonacci linear feedback shift as a transpose of a Galois linear feedback shift also helps you in a lot of proofs and finding things like that, because you can use a lot of properties of finite fields. So we define the affine Galois linear feedback shift, f alpha beta, in the same way that we define the Fibonacci linear feedback shift. At each stage, we just add a beta to it. So we have another nice fixed point theorem, not fixed point theorem, orbit translation theorem, that if G alpha beta is invertible, sorry, it should be Galois linear feedback shift, such that the sum of alpha is equal to the sum of beta is equal to 1. Then for every orbit of f alpha beta, there's an orbit of f alpha en such that it's a translation. So even though we have all these other analogous results, we don't get a nice analogous result of the equal expected value homomesy theorem. So one thing I'm pretty confident of is that we still need this condition to get the equal expected value homomesy. That when we take the irreducible decomposition of p alpha of x, the multiplicity of x minus 1 should still be 2 to the m. And the multiplicity of x minus 1 should still be the highest multiplicity of our polynomial. But the other condition, that there has to be a different condition that's modulating whether it's an equal expected value homomesy. But one thing we do know is that if you take alpha check, so remember that alpha check is just the it is a while back in the talk. Alpha check is just replacing alpha with the partial sum of alpha starting at that element. So it turns out that whenever alpha check is equal to 1, that indicator function is 1/2 messic. So we have an example here. So p alpha of x satisfies our condition. And when alpha is equal to 0, 1, 1, 1, beta is equal to 0, 0, 0, 1, then alpha check is equal to 1, 1, 0, 1. So if you pay attention to the first, second, and fourth column, you'll see that they're all 1/2 messic. But the third column need not be. In this orbit, you have an excess one, a number of ones, and in this column, you have an excess number of zeros. So it doesn't quite work. But it's not that you can never get the equal expected value homomesy whenever alpha check isn't all ones. It's if I just took alpha is equal to 0, 0, 1, 1, 1, and beta is equal to 0, 0, 0, 0, 1, then G alpha beta exhibits the equal expected value homomesy. So yeah, the Galois action acts a lot more sporadic than the Fibonacci action, but it'd be interesting to know if there's a nice polynomial condition, or maybe the condition is a bit different to whether it exhibits the equal expected value homomesy. There are a lot of tricks we can't use because instead of being a local action, this is more of a global action. Okay, so just one last orbit. It's not a linear feedback shift. It's just the ASCII version. For thank you. Thank you for being here.
Let's thank Chinmay. And it's time for questions. You're welcome to unmute and ask the question or put your question in the chat.
Yeah, I have the chat.
Hi. My first question is, what are some applications of homomesies?
Yeah. So homomesy is really nice. Usually they've been studied in row motion. So the way I've always thought of applying homomesies is that it tells you something about the orbit. Like here we found a homomesy, and what we actually saw happen is that the orbit is exactly reflected halfway through. As for other applications of homomesies, I'm not quite sure. I think it's an interesting thing to study. I see Mike Joseph in the chat, so I know he's worked with homomesies a lot longer than I have, so maybe he'd be a better person to ask. But yeah, I think it gives you like a richer understanding of the action. It's also linked to the cyclic sieving phenomenon. Um, a lot of the times when you find a homomesy, there's also a cyclic sieving going on in the action. But yeah, that's a great question. Thank you.
More questions? I wanted to know if the irreducibles themselves play a role in your analysis. Like if you look at the eigenvalues of your matrix, does that tell you anything?
Yeah, we did look at the eigenvalues for a bit, but mostly in the context of the Fibonacci linear feedback shift, and that didn't really tell us anything. But for the Galois linear feedback shift, I wouldn't be surprised if there's something we're missing. Maybe the irreducible factors do play a role.
Mm-hmm.
Yeah, so maybe it's time to go into like some finite field theory. I'm not sure just yet. I'm hoping there's a polynomial condition. Right now, it seems pretty random. For example, something I didn't put in because I'm not sure is that whenever whenever n is 1 mod 4, then the whenever your alpha is 0 generally works, gives you the equal expected value homomesy. But whenever it's 3 or 2 or 0 mod 4, it doesn't. Whenever it, yeah.
Interesting.
Yeah, so that does kind of like hint to some sort of algebraic condition, but I'm not sure myself. But yeah, that's one thing to look at. Definitely the actual irreducible factors.
Also, do you know anything about pairs? That if like so looking at a column, have you looked at like 0, 1, 1, 0, and then how they appear? Do they also show complement behavior?
That's a really good question. So it's actually relevant in the Galois case because when you look at the Galois case, when like certain pairs are homomesic, that's exactly when EEV is exhibited. So let me try to so in this case, whenever you look at the pair of chi1 and chi4, so here we have 1 1 and 0 0. If the one if let me try to think to make sure I don't say anything wrong. I think it's whenever the 1 1 0 0 pairs appear at the same amount as the 0 1 1 0 pairs, you get the equal expected value homomesy. So if we knew something about like the pairs, then we'd be able to crack the Galois thing.
Okay.
But yeah, so that's a really good question. Yes. But yeah, so
pairs sort of correspond to multiplying or adding.
yes, they do correspond to multiplying, and that's part of the challenge we have here because sorry, I'm going back so far. I can't. Yeah, here, right? I should have mentioned this when I got to the slide. This is the only part of the talk where we're actually doing arithmetic in a field of characteristic 0 instead of a field of characteristic 2, right? But because everything was just like adding two things or adding one things with zeros and ones, we are like able to like kind of shift between them seamlessly. But when you add multiplication, it becomes a lot harder to like do all those like tricks. Yeah, no, thank you for the question.
Are there any more questions? If not, let's thank Chinmay again. Great talk. And I'll stop the recording.